In today's video, we are going to explore the motor effect, which is a fascinating phenomenon that occurs when a wire carrying an electric current is placed within a magnetic field and as a result experiences a physical force. We will learn how this force comes about, how we can determine the exact direction in which the force acts, and how to calculate the strength or magnitude of this force. Previously in our discussion on electromagnetism, we discovered that any wire carrying an electric current will generate its own magnetic field. This means that if we now place this wire in the space between the north and south poles of two separate magnets, we create a situation where the magnetic field produced by the wire interacts with the existing magnetic field of the magnets. This interaction leads to a resultant force being exerted on the wire, effectively pushing it in a particular direction, which is often out of the magnetic field area. However, for the wire to experience the full and maximum possible force, it must be positioned at a perfect right angle that is 90 degrees to the magnetic field lines. If the wire is only at a slight angle rather than a full right angle, then the force it feels will be smaller or weaker. On the other hand, if the wire is aligned in the exact same direction as the magnetic field, then surprisingly, it will not experience any force at all because there is no component of the magnetic field acting perpendicularly on the current. In order to determine the direction of this magnetic force, we need to consider two critical aspects. First, the direction of the magnetic field, and second, the direction of the current flowing through the wire. To help us with this, we use a helpful rule known as Fleming's left-hand rule. This method involves holding up your left hand in a very specific way. Your thumb must be extended upwards, your first finger must point forwards, and your second finger should stick out to the side at a right angle. In this configuration, the first finger represents the direction of the magnetic field, which always goes from the North Pole to the South Pole. The second finger indicates the direction in which the electric current is flowing through the wire, and whichever direction your thumb is pointing in will show the direction of the force that the wire will feel due to this interaction. It can feel a little awkward or confusing at first to position your hand in just the right way, but with some practice and maybe moving your arm or body to help orient it, you'll be able to figure out the direction of the force with confidence. Another very common example where we can observe the motor effect in action is within a setup that uses a horseshoe magnet. In this case, we place 3 parallel metal rails between the north and south poles of the horseshoe magnet. The 2 outer rails are fixed in place, but the third rail, which connects the two, is free to move or roll. When we switch on the power and allow current to pass through this rail, it generates its own magnetic field. This field then interacts with the magnetic field from the horseshoe magnet, creating a force on the moving rail. To determine the direction in which this rail will move, we again turn to Fleming's left-hand rule. Since the magnetic field is going vertically downward from the North Pole to the South Pole, your first finger should point in that direction. If the current is flowing in a direction towards your body, your second finger should point towards you. At this point, your thumb will naturally point to the right, indicating the direction that the force is acting, and therefore showing you that the rail will roll to the right. Now, let us talk about how we can calculate the strength of the force felt by the wire due to this effect. As long as the wire is placed at a right angle to the magnetic field, we can use the formula force equals magnetic field strength multiplied by current multiplied by the length of the wire. Written in words, the force in newtons is equal to the magnetic flux density measured in Teslas multiplied by the current in amperes multiplied by the length of the wire in meters. This equation is usually provided to you during exams, so you do not need to memorize it, although it is helpful to understand what each term represents. For example, let us suppose we have a piece of wire that is 10 centimeters long, and it carries a current of 5 amperes. We place this wire into a magnetic field with a strength of 0.4 Teslas at a perfect right angle. To calculate the force it experiences, we first convert the length into meters, which means we divide 10 centimeters by 100 to get 0.1 meters. Then we substitute the values into the formula, multiplying 0.4 by 5, and then by 0.1, which gives us a result of 0.2 newtons. This means that the wire would experience a force of 0.2 newtons, pushing it in the direction determined by Fleming's rule. That brings us to the end of today's lesson on the motor effect. We hope you found it informative and helpful. It is a powerful concept with many real-world applications, particularly in electric motors and magnetic devices. Thank you so much for watching, and we will see you again next time with more helpful explanations and examples.